In this video, we examine the concept of outliers and their related issues. There's a number of reasons why outliers may occur in a dataset. First of all, errors are not all that uncommon. They may have happened while you were conducting the study, or they may be typos as you were recording the data. They may even occur during the data analysis stage. If you know that the outlier is actually an error, then you can discard the value, or if you are lucky enough to have access to detailed records, then you can correct the value. Outliers, however, can be also legitimate values that simply represent the extent of the natural variability of your population. As such, they provide important information about the location and spread of your variable and should not be discarded. Sometimes, though, the outliers correspond to individuals that are not fundamentally representative of your intended target population. And that's when it's really important to have a good understanding of your end objective. Do you wish to describe a whole population without exception, in which case unusual observations are just part of it? Or is your intention to describe what is fundamentally the core of your target population? In that case, you can discard outliers if you acknowledge their presence in your dataset and you explain the reason for excluding them from your analysis. Looking back at our UCI student survey data, we have here a dot plot displaying the answers to the survey prompt, enter your height in inches. Nearly all values are larger than 50 inches, but we see two extremely small and biologically impossible values, 5.3 and 6 inches. Clearly, those are errors, but because the survey was anonymous, there's no way for us to go back and double-check on those values. Therefore, those two extreme values should be discarded. But let's look at the impact they have on summary statistics. Obviously, the minimum is hugely impacted since those two outliers are the smallest values. But the rest of the 5-number summary is barely affected. On the other hand, the mean and standard deviation are noticeably different with and without the outliers. It's not surprising considering that those summary statistics use all of the values in the dataset in their computation. So if you had summarized the mean height of the students in this survey as 64.8 inches, you would have understated the true mean height by nearly a whole inch. Yet notice that the value 64.8 is not in itself an impossible value, which means that if you had gone straight from collecting the data to calculating and reporting the mean, you may not even have noticed that there were fundamental problems with your data. Which brings us to this very important lesson. Always plot your data before doing any further analysis. The US Current Population Survey has data on the percent of the population in each state who is under the age of 18. The individuals here are the 50 states, and we have a quantitative measure for each one, the percent of their population who is under the age of 18. Therefore, we can plot this quantitative variable into a dot plot or a histogram, as shown here. The distribution is single-peaked, roughly symmetric, and has a clear outlier. That outlier is the state of Utah, with 29.8% of its population being under the age of 18. Now, this is not a mistake, it's simply a documented fact. And if you want to describe the United States, then you must also include the state of Utah, even if it's an outlier. If you do a lot of data analysis, you may need help noticing outliers. We are going to describe an automated method that helps us flag suspected outliers. We start with the definition of the interquartile range, the distance between the first and third quartile in a dataset. Then we define a value as being a suspected outlier if it falls outside of the range defined by 1.5 times interquartile range on either side of the first and the third quartiles. It's very important here to understand that this is showing us only suspected outlier. It's only a flagging mechanism. It is not a definition of an outlier. The only way to tell whether a point is or isn't an outlier is by looking at how it fits with the rest of the data. Going back to our UCI student dataset, here is the distribution of body mass index values in this survey. The data can also be shown in a box plot. In a regular box plot, the whiskers extend all the way to the minimum and the maximum. In a modified box plot, by contrast, any value that would fall outside this 1.5 time interquartile range from the quartiles would be shown as individual dots instead, just like in a dot plot. So here we see that 3 data points have been flagged as suspected outliers. When you look at the histogram, we only seem to have a right skew in the data and no outliers. When you look at the dot plot, you can see that those 3 values are a little bit further away from the rest of the dataset, but really overall they are part of that right skew. So you may argue that those are very mild outliers, or you may argue that they are just part of the skew. It is not because they fell outside of the 1.5 time interquartile range that they are outliers. That determination can only be made by carefully examining the dataset and then deciding whether you think that those are clear outliers, potentially mild outliers, or not outliers. How do we deal with outliers? Well, outliers can be a mistake, or they can be real but unusual values. So it is critical to investigate outliers if you find them. Are they realistic or even possible values for your variable? Check your data collection logs. Look at other related variables in your dataset and see whether the values you found make sense in that context or not. In the end, you should not throw out an outlier without very careful consideration and a clear justification for doing so. Also understand that many numerical summaries are affected by outliers and may become misleading if you include values that should not be present in your dataset. And lastly, we will see later on that some common inference procedures do not handle skew or outliers very well under some circumstances. So it's important to know whether or not you have any outliers. We have a dot plot of data from the Michigan Department of Environmental Quality showing the distribution of water lead levels in a random sample of houses in the city of Flint right after the city switched its water source in 2014. We see that the distribution is single-peaked, very clearly strongly skewed, with a number of unusual data points, including one extreme outlier at more than 100 parts per billion. At the time, 2 of those data points shown here were initially thrown out for being suspicious. Placing them in historical perspective, we now know that those points were actually symptomatic of new and serious lead level contamination issues. The EPA, the Environmental Protection Agency, has clear rules regarding what must be done in situations indicating high lead levels. Specifically, when more than 10% of houses have high level of lead in excess of 15 parts per billion, then action must legally be taken. If all the values collected in Flint had been included in the analysis, more than 10% of the houses would have had that high level of lead, and therefore action would have been taken. But because 2 of the data points were excluded, the overall percent of houses with high lead levels remained under 10%, and nothing was done at the time.